What we're going to look at today are ultimately our acids and bases. We talked about our intermolecular forces and how those can be used to predict different properties. Okay? The two biggest properties that are coming from your intermolecular forces that you will see probably on the final would be your phase transitions. What phase transitions are going to be dependent on intermolecular forces? Melting point, boiling point. The stronger the intermolecular force, what does that do to the temperature required to break it into a liquid or to a gas? It increases it. So all of your phase transitions are dependent on intermolecular forces. The other common one to see would be solubility. Okay? Both of those are really big questions that go back to the same idea of intermolecular forces. Solubility, there's an extra little rule to it. What's our extra little rule with solubility? Anybody remember that one? Kinda. Like forces dissolve like forces. So if you have similar forces within the molecule, we would expect it to dissolve. Okay? The last one, which might show up, I may have just been looking at other problems. You might see a question on vapor pressure based on intermolecular forces, but I kind of doubt that. Okay? So you won't see a whole lot there. So the idea is, how do you apply the intermolecular forces into each of these physical observables? What we ended up doing, particularly when we looked at solubility, is that we can now dissolve compounds in a solvent. Primarily, our solvent is water. And this becomes important because when we go through and run a reaction, we need to make sure that each of our reactants has the ability to interact with each other. If they never get close enough to each other, they can never start to interact, which means they can never start to make a bond. So we tend to use a solvent, some kind of solution, to get those solid species up into a form where they can now interact with each other and potentially make products. Okay? Change that bond structure. Okay? So to go through and do that, we have to add that solvent. What solvent do we typically use, at least as far as you guys are concerned? Water. It's the most common solvent for everything, really. Okay? So we end up dissolving each of our solids into a water solution. We then mix those solutions and see if a reaction occurs. Okay? What's something that you could notice if a chemical reaction occurred? What would you see or feel? We could see a temperature change. That's a good symbol for a chemical reaction. We could see a phase change, which is what I think you mean by physical change. If we see a phase transition, two liquids, now all of a sudden we've got a solid, that's a phase transition. That is a symbol or something that we can use to monitor the reaction. Okay? So we have water involved in this reaction. How do we know water is in this reaction? Well, it says solution. That's one option. I can see that. We ignore everything else and just look at that reaction equation.
Aqueous.
It says AQ. AQ means aqueous, or water. Aqua for water. Okay? It means water. It does not mean liquid. Liquid is an entirely separate thing. You've got to be very careful with that. Okay? A liquid is a pure substance that is in a more mobile state. Okay? Aqueous means that we have water and something is dissolved in that water. Okay? So those are two entirely separate phases. Okay? So if we take a look at our aqueous solutions, we now have water present. Is water reacting? Why not? If we look at the balanced equation, does it show water? No. It just shows that water is present by saying it's aqueous. But water is not necessary to make silver bromide or to make the aluminum nitrate. Right? So water, while being part of our reaction mixture, doesn't actually do anything to make that chemistry occur, at least at a first approximation. Okay? Why does that become important? Well, that comes back to that last question there. How do we quantify the amount of silver bromide that we make in this reaction? So what does quantify mean? can we put a number on it? So how would we measure the silver bromide? In the lab, easiest way to measure the silver bromide. Weigh it. Okay? And we can weigh it because silver bromide is a solid. Everything else is aqueous. So if we mix these, we get the solid to form, and now we have a bunch of aqueous stuff floating around. How can we separate that solid away from the aqueous? How do you separate any solid from a liquid? Filter. So we can filter that out, and we now have solid silver bromide. We can weigh that. We know that is silver bromide. There's nothing else there. Fantastic. We get an actual way to quantify it. But now the question, where did it come from? Okay. That silver bromide came from our aluminum bromide reacting with silver nitrate. How much of that silver bromide should we have made? Well, that's going to depend on how much aluminum bromide and how much silver nitrate we started with. Well, how much did we start with? How are we going to measure those? Okay. Those are solutions, aqueous solutions. So if we go to weigh them, what are we weighing? We're going to be weighing aluminum bromide and water. So we can't do a molar mass conversion with that to get into moles because the water isn't involved in the reaction. And that's going to alter that mass amount. Okay, well, maybe because it's a solution, we can measure the volume. But then the volume is a measure of what? The aluminum bromide and still water. So we've got a problem. Okay, the problem is that we can't figure out how much of just that aluminum bromide is present because it's already dissolved in water. We have to somehow come up with a way to subtract that water out, find some way to negate its effect or relationship in the experiment. Okay? To do that, we've got a couple options. We could go back to percents, as we saw in Chapter 2. We could say that that solution was a percent aluminum bromide per the total mass of the solution. So we do a percent by mass. Or we could do a percent by volume. All of those are perfectly valid things to go through and use. We end up not using them. Any ideas why? What unit is a percent? Nothing. It's just a percent. So if we're going to try and convert aluminum bromide over into our product, and our percent is unitless, how can we do that? It's kind of an odd situation. So what we want to come up with is some other way to measure how much aluminum bromide is in that solution. Okay? And the way we're going to do that is instead of looking at a percent, look at something known as the molarity. Okay? We're looking at the molarity of the solution, which is just a fancy way of looking at our concentration. The issue with molarity that I think a lot of students have is it's always written as this capital M. Right? The only reason it's written as the capital M is that if we're going to type up a label, it's a lot easier to just write a number in capital M than it is to write a number of moles per liter of substance. So what we've done is simplified how we write out the concentration to help us kind of get through it a little bit easier and report it easier. Ultimately, when you're going to run a calculation, capital M is a useless unit. How many other times have you seen capital M show up? Okay, lots. Where? Where does capital M show up any other place than molarity? Did you say Mike?
It can be confused with a meter, but
That's not capital M, that's lowercase m. Okay.
Yeah, mega's a capital. Yeah, because micro's
Mega what?
megagrams.
Megagrams. It's not capital M anymore. That is now the symbol for mega of another unit. The capital M unit for molarity never shows up. Whereas, have we seen the mole unit show up before? Can we relate the moles to anything else? Say grams through, say, maybe a molar mass? Yeah. Could we relate the moles to, say, the number of atoms through Avogadro's number? Yeah. There's plenty of ways that we see moles show up. That shows up in a ton of different possible conversions. The molarity unit itself doesn't show up. The only reason we use it is because we don't want to write out the full meaning of the molarity unit. Which means when you have to work with it in all of your calculations, capital M does not work. When you see that capital M, you must immediately convert that into a unit system that makes sense. That unit system is moles per liter. Okay? So if I tell you you have a 2 molar solution of NaOH, so what you could see on the bottle might be 2M NaOH. What does that mean? Well, capital.
You have 2 moles per liter.
Almost. Very, very close. I'm going to get nitpicky. 2 moles.
Per liter of solution.
Better on the bottom. Liter of our solution, and on top.
2 moles of substance per liter of solution.
And our substance in this case would be our NaOH.
God.
Yeah, I know. It's tedious, right? You need to keep track of that full unit on what those things are. Otherwise, you can't track your units. The units can't solve your problems. Okay? So what we have to do is whenever you see that capital M, immediately convert it across. Okay? The number is going to be the number in front of your moles. Why do we put the 1 in front of liters? Because we don't want to change the number in front of moles. Okay? So whenever we're writing it out, it is always the number of moles in the 1 liter of a total solution. Okay? I can then take a small volume of that solution and the concentration stays the same because we assume it's evenly mixed throughout, which can be a dangerous assumption. Okay? So let's look at a couple problems that work with molarity. Okay? I will note that the slides have another much more difficult molarity problem that's kind of the long extended one, like your percent yields or limiting reactants. We won't go through and do that one in class today because there's other more important topics. So we're focusing more on what you would need for the final. Okay? So what is the molarity of a solution containing 24.0 grams of NaOH in a 0.100 liter solution? Yeah, liter solution. So what is our molarity? What are we trying to solve for? We want the molarity of NaOH. Anytime you see the capital M, you should rewrite it as the moles of our substance, in this case NaOH, per liters of our solution. Okay? We don't want to put in the 1 liter yet because that's going to be dependent in this case on the volume of our solution. Okay? So, first way to approach this is to solve it in what I would argue are 3 pieces. Number 1, solve for the moles. Number 2, solve for the liters. Number 3, divide the 2, and we now have our final answer. Okay? That's how most people go through and solve this one. I would argue that's probably how I would go through and solve it as well, except this morning for some reason I decided to do it in 1 line. Okay, so let's leave a space for the 1 line calculation. Now let's attempt to go through and solve this now. So, said we had 3 possible steps. Let's do the moles first, and then the liters second. So, our first calculation, I want to figure out the number of moles of NaOH. So that needs to be my answer. Do I know anything about the NaOH to start with? Yes is a good answer. I've got 24.0 grams of NaOH. Can I convert grams into moles? Okay, how do I do that conversion? What unit needs to show up on top? What unit on the bottom? Moles needs to be on top. Why? But grams have nothing to do with moles. What was your answer? We want our final answer to have moles on top. Okay, it needs to be in the numerator, so that's why we want moles on top. Why do we want grams on the bottom? The grams need to cancel out with our other unit. What is the relationship between the grams of NaOH and the moles of NaOH? Where is that information found? From the periodic table. We go through and add up the molecular weights for each of those atoms. And if I did it right, I think it's 1 mole is 40 grams. Don't tell me 39.998. I know. We're rounding. Okay. We could then enter that into our calculator and we get the moles of NaOH. There's step 1. Really helpful. But our answer is moles over liters. So what we need to do is figure out the liters of NaOH in our liters of solution. Okay, so what's our answer need to be as far as units? It needs to be liters of our solution. Do we know anything about our volume of our solution? We start with 0.100 liters of solution. Do we need to do a conversion? Why not? Look at our units. Liters of solution versus liters of solution. We have the volume. It's solved. Done. No conversions. Nice. Our very last step, which I'll put up here in orange, is to actually solve for our molarity. To solve for the molarity, it's the moles of NaOH, right, which if you punch that into your calculator, in theory comes out as 0.600, if we're going to be picky, moles of NaOH divided by, what's our liters of solution? 0.100 liters of our solution. Yes, we could absolutely report it as this. But when you get your income reported, is it reported as a fraction? No. It's always reported as a number, a decimal value. Why? It's a little bit easier to look at a decimal value than it is to look at a fraction. So what do? Do the division and convert it into that decimal value and get us into that moles per liter, also known as our molarity, and we should get 6.00 molar NaOH. Okay? So 3 individual steps. Okay? It works. I will admit that this is probably how I would go through and solve any molarity question, breaking it into 2 steps. We could very well do it in one complete, smooth, full line if we really wanted to. So let's go back and attempt that. Our answer needs to be moles per liter. And whoops. What's wrong with what I just wrote? And I'm now going to erase. I know you were all watching everything I wrote, so you saw exactly what was there. I need to specify the substance, right? Moles of our NaOH. What information did we start with? Grams of NaOH and liters of our solution. Okay, so we got 2 approaches on where we can start. We could start with our liters or we could start with our grams. Which do you want to start with?
Grams.
Okay, grams. Where should our grams of NaOH show up? Numerator or denominator? Why do you want to put it in the numerator? I don't see grams in my numerator. Okay. What we're going to look at is if we start with our 24.0 grams of NaOH, we do want that in the numerator. The reason it's going to go in the numerator is not because our gram and mole unit match. Hopefully that'll catch up in a second there. But the substance unit matches. Where does the NaOH show up? In the numerator. Which means when I start my calculation, where should the NaOH show up? In the numerator. Otherwise, I'm going to end up putting it into the wrong spot. Okay? What unit do I want for my NaOH? Moles of NaOH. Does that equal grams of NaOH? No. So we're going to have to do a conversion. That conversion needs to get rid of our grams of NaOH, and we need moles of NaOH. What's the relationship between those two? 1 mole is 40 grams. If we track our units, grams of NaOH cancel. We're now at units of moles of NaOH. Darn close to our final answer, but not perfect. Our final answer is moles per liter. Okay? So I now need to do yet another conversion, sort of. It's not really a conversion. Somehow or another, what needs to show up in the denominator? Liters. What needs to show up in the numerator above this liters? The number 1. No units. Why is there no units? We already have the units set up. We are not doing a conversion. What we're doing is a calculation. We just happen to put that calculation in our conversion setup. If you compare the total calculations done in orange versus the calculations done for steps 1, 2, and 3, what's the difference? Step 1, what did we do? 24 divided by 40. What's the first calculation in our orange? 24 divided by 40. Step 2, we didn't do any calculations. It directly went straight across. What happened in step 3? We took the answer from step 1 and we divided by 0.1. What's that last calculation do? Divide by 0.1. All of the calculations are done exactly the same. We, instead of putting them into 3 individual sections, ran it as one line. Okay? That can make your calculations easier to work with, easier to get through. Okay? Depends on what you're used to. There are a variety of other methods for going through and doing these unit conversions. Some of them work exceptionally well. All of them are ultimately variations off of the same theme. Right? All you're trying to do is get your units to match the answer and make sure that you don't introduce new conversion factors along the way. Right? Test you guys on it. Boom. That would have been nice to record. Okay? So, now what I'm going to do is compare. Now that I've picked something to work with. Okay? Do I want moles of potassium dichromate? No, I want grams. Can I convert my moles into grams? How can I do that? I can pull up the periodic table, add up the molecular weights of those compounds, and get that relationship. That relationship is 294. Thank you. Did I hear a 0.24? Okay, let's just do 0.2 per 1 mole of potassium dichromate. What does this do with my units? The moles of potassium dichromate cancel. What do I now have as units? I have grams of potassium dichromate per 1 liter of the solution. Is that my final answer? No. I don't want liters showing up in my answer. So somehow or another, I'm going to need to cancel that unit. Okay? So I'm going to have to do some other work here. That other work needs to be getting rid of the liter solution. So I could predict that I need to multiply by liters of my solution. Do I have liters of my solution? Think about it first before you write it. No, I have milliliters. Okay, so I can't multiply by liters of the solution because I don't have liters of the solution. I could multiply by milliliters of the solution. I'm at least getting the volume set up where they could cancel. I just have the wrong units. Okay? What number would I put in front of milliliters? 125.0. What's the number I put underneath? 1. I know where you're getting 1,000 from, but that's not the relationship here. This is 125 milliliters, period. It's not a conversion. There's not a relationship to anything else. There are 125 milliliters. So we will put it over 1. Do my units cancel? No. So I need to do a conversion factor to get rid of those units. I need my liter unit to cancel, so it needs to show up on top, so it cancels with the denominator. I need my milliliter unit to show up in the denominator, so it cancels with the previous numerator. What's the relationship between liters and milliliters?
1,000 milliliters.
Okay, you guys must be talking to other people because I'm definitely not teaching you 1,000 milliliters. We can say 10 to the minus 3 liters is 1 milliliter. There are other conversions that work absolutely equally well. I'm perfectly all right with those. I just don't like them because that's not how they've been shown in the textbook. So I'm trying to be as consistent as possible. The other conversion, 1 liter, could say 10 to the third milliliters. 1 liter is 1,000 milliliters. All of those are equally valid. The reason why I don't like that method is that we now start changing the number in front of our prefix unit as opposed to always changing the base unit. Okay? So it can make it easier to get some of the other conversions confused. Okay? So the idea, write down what you want and then pick some place to start. If you put it together wrong, as long as you track your units, you should see that you end up solving for the inverse. Maybe you said that you wanted to divide by the molarity. Okay? So that means liters are on top, moles are on the bottom. When you went through to solve your answer, your final answer for units would be 1 over grams. So if you do the inverse of your answer, you'll get the correct one. Follow the units through your problem. They will solve problems for you. Okay? Where it becomes an issue is when you think you know it correctly. Okay? And as long as your think is correct, that's good. If your think happened to make a simple mistake, say, oh, I just need to multiply by 1,000, what happens? You got the wrong answer. Okay? So this is why we do dimensional analysis. You do not have to think. Chemists are stupid. Okay? And I was recording that one. That was great. Okay? We don't want to think. We want to let everything else solve it for us as best we can so that we can save our brain power for when we actually do need to do comparisons and conversions. Okay? Questions about your molarities? 42. That was a joke. I don't know. Who solved it? I think I heard numbers in the 5 point.
I just want to check mine.
Yeah. 5.52?
Yeah.
52 grams. Yeah. Okay. Questions about that? And good. I heard everybody say 5.52. That's good. Okay. So it sounds like you got conversions down. So let's do something entirely different. Yeah, lucky you. Solution simplifications. If you think to the labs that you guys have done, I don't know how, is it Dr. Huber? Or does he go by Mr.?
We just go with
Huber? Okay. I don't remember, or I don't know how Huber is teaching the labs. If he's not been told anything like I've been, you haven't been made to go through and do this kind of format. You guys heard of total ionic or net ionic yet? No, okay, that's nice. So he's same position I am. What we can go through and do is simplify things. Think back to your copper lab, the copper ore. You were asked to provide a balanced equation. Okay, the balanced equation that you hopefully wrote had the bones of copper plus 2 plus aluminum went to aluminum plus 3 plus copper. Vaguely sound familiar?
Yes.
Okay. Then you had to go through and balance it. All right, well, what type of reaction was that? Single replacement. In a single replacement reaction, we exchange one ion and put it into a compound. What's the compound in this equation? Well, it's simple. Your compounds are where we have two of more than one element, right? So where's the compound? Oh, that's kind of odd. Why did we not show that compound? That's because in the course of this reaction, what were we concerned about? We were concerned about converting copper ion into copper metal. Do I care what the compound is? No. I only care about the copper metal. So when I write out the reaction, the only thing I'm going to write in my reaction are the things that contribute to making the product that I want. Okay? You might regret it after you see the middle step. Okay? So what we're going to go through and do is take a look at solution chemistry. And this is why we saved it for solutions. We can take a balanced equation, and it does need to be balanced before we start, and we'll look at it and say, okay, what parts of this just aren't going to be important? Well, in this format, is it obvious which parts aren't going to be important? Not really. So what we're going to go through and do is take these compounds and in certain cases turn them into the ions. When can we turn something into an ion? If we dissolve sodium chloride in water, what happens? Dissolves, kind of works. Instead of having sodium chloride, we have sodium ion and chloride ion floating off on their own. So if we have an ionic compound dissolved in water, we can separate it into the ions. How do we know it's dissolved in water? It says aqueous. So any place that we see aqueous, we can separate that compound into the individual ions. So here's where it becomes fun, and where I distinctly dislike it. So I'm not calling it fun. That was sarcasm. Okay? So aluminum bromide. The ions that we've got are aluminum with what charge? +3. It is now separated from the bromide. So it's aluminum +3, aqueous. So we have to specify that charge. Plus what? Well, the other part of the name was bromide, so we can draw bromide. Again, aqueous to specify its phase. What was that? I heard you.
Don't you put the 3 in the front of the bromide?
Why do you need to put the 3 in?
Because there's 3.
To balance our compound, our molecular formula was aluminum, or AlBr3. That 3 meant there were 3 bromides per aluminum. When I take that compound and turn it into the individual ions, guess what happens? We get the individual ions, so we get 3 bromides. Where do we put that 3? We have to put it in front. If we put it afterwards as a subscript, what are we saying? We're saying it's still together and it's now a compound or a complex ion, polyatomic ion. We don't have that as a polyatomic ion. Okay, I'm going to run out of space really fast. So that's our first one. We can move to the next compound. Silver nitrate. Is that aqueous? Yep, so we can do the same thing. I'm going to need a little more space there. Silver ion has a +1 charge, aqueous. And we have, what was it, nitrate? -1 charge, aqueous. Yes, you need to know all those charges. Do you have another objection in this one? Anybody else have an objection in this one? Yeah, what was the objection? I see the hand. The 3 in front of the silver nitrate applies to what? Everything after it. Which means I don't have just 1 silver ion, I have 3 silver ions. I don't have just 1 nitrate ion, I have 3 nitrate ions. All right, now we've done all the reactants, so we can go ahead and take a look at the products. First one, silver bromide, what kind of bond? It's an ionic bond. So let's turn it into the ions. Can't because it's a solid. The only ones we can split into ions must be aqueous. If it does not specify aqueous, you cannot touch it. Which means what I would write would be 3 silver bromide solid. And I would move to the next species. The next species is aluminum nitrate as aqueous, which means I can turn that into an ion. Aluminum plus 3, wow, I actually fit it in this one line. 3, sort of. Nitrate, aqueous, and we have to put the 3 in front because, okay, the 3 after it as our subscript. Why does the 3 in the nitrate not come forward? Now that orange 3. That 3 is necessary to make that nitrate. We didn't separate aluminum into A ions and L ions. It was aluminum, Al plus 3. Okay, so what we now have is the total ionic format. Okay, very tedious to draw out, but that sets us up for this last part, which is where we can now go through and simplify this reaction down to just what occurred in the course of the reaction. Okay, think back to everybody's favorite chapter, our redox, in particular balancing our redox. One of the methods was looking at the electrons and making sure that we had the same number of electrons produced as consumed. Why? What could we do with the electrons if they were both produced and consumed? We can cancel them. They show up on both sides of the reaction. We're going to do the same thing here. So let's start. Aluminum plus 3 aqueous. Does that show up the same on both sides of the equation? Yes, which means I can cancel that term. I don't care about it. Bromide. Do I see bromide ion on both sides of the equation? I see the Br in there. Why can't I cancel that Br? It's not aqueous, so the phase is wrong. Also, the charge is wrong. For that matter, the compound's wrong. Okay? That's not bromide on its own. That is silver bromide. Okay? So I can't cancel the bromide. So what I'll go ahead and do is write it down below. And I will translate the coefficient with it. Okay? What happens with the silver? Silver ion. Does that show up the same? Does not show up the same because in one case it shows up in a compound. So 3 silver aqueous. Last part, nitrate. Those show up the same on both sides. And not only do the nitrates show up the same, but we have the exact same number of both, so they entirely cancel out. We've now canceled everything that we can. There's our reaction arrow. 3 silver, bromide, solid. We've now narrowed down our molecular format down to the bare minimum of what exactly had to happen for that reaction to occur. Okay? What we have there is now our net ionic format. It's kind of the bare bones minimum of what's going on with it. That's what you did within the copper lab, and I think you did it. No, maybe it's just the copper lab. I thought there was another one. Okay? So we simplify that down to the absolute bare essentials. Okay? Why is it a pain to get to that format? Well, we had to go through and write out our total ionic format. Those of you moving on into other chemistries, like general chemistry, 151, okay? The reason that this format becomes so irritating is you'll notice that I specified the phase for each of these all the way through. Is it necessary to specify the phase? You have to specify that phase so that you know that you can cancel it. Some instructors are extremely, ridiculously strict about that. All right? So you need to watch for those phases. They must be specified in all reactions. Okay? Questions about our simplifications? Okay. So the next part about this is our acids and bases, trying to get into what we can do with these when we put them into solution. Make one little change. What's the name of our first compound? Dihydrogen sulfide would be good up to the point that I put in AQ. We have a hydrogen and aqueous, which means it's an acid. Now we'd have to go through and make sure we name it appropriately. Is this a binary or a ternary acid? Binary, because we're looking at just 2 elements, which means when we name, we have to use hydro as our prefix, and we get hydrosulfuric acid. We take a look at that last one. What's that one called? It's a ternary acid, so no use of the hydro. We name it after the complex ion. So we've got sulfate. The 8 turns into an ic acid when we're making an acid, and we get sulfuric acid. Okay? I mention it because H2SAQ and H2SO4AQ have very easy to confuse names. Okay? And all of it spins on knowing your nomenclature rules for binary versus ternary. Okay? Why do we even come up with that whole new nomenclature system? Why bother to call them acids? Why not just call them what they are? In that first one, dihydrogen sulfide. In the second one, dihydrogen sulfate. Or actually, we can get away with hydrogen sulfate. Why do we have to call them acids? Safety is part of it. Okay? Acids have a very different chemistry than we've seen in other species. Okay? So why do we get these names? Is ultimately to separate them out and classify them under different rules. So I would argue that we weren't initially looking at scientists, but observationalists. People that went through and made some simple observations behind different materials. And two primary observations stood out. Some chemicals tasted very sour, which we never do now because we never taste chemicals, okay, legally. We get sour tasting chemicals, and we also have this weird slippery feeling, okay? Sour tasting chemicals are typically found in what kinds of compounds? Acidic compounds. That sour taste is due to an acid functionality. How about the slippery feeling? It's the base. Okay? I don't know what's going on with milk. What about milk? Yeah? Maybe we can talk about that more afterward. Okay? So we've got that slippery feeling. If you ever got some base on your hands, what do you end up noticing when you rub your fingers together? Kind of slips and slides. Why does it slip and slide? I've heard this, I don't believe it, but you get a strong base in your hand like sodium hydroxide and you run it between your fingers, you will feel it start to slip and slide. Why is it slippery? That base is reacting with the fat in your skin and turning your skin into soap. That soap, in very minimal extent. It can be a real thing to a certain extent, but not to the extent for all bases. I don't buy that.
At least for water, if you have skin compressed under certain pressure for a long matter of time, your skin will actually turn soapy.
Oh, well, that's absolutely true. Yeah, that's a different process, though. But yes. So we can take a look at these reactions, and one of the secondary effects behind these observationalist things is not only did we get these sour tasting and slippery feeling chemicals, but then when someone got the crazy idea to mix these things, we also noticed some interesting observations. What was that interesting observation that they noticed?
They died because they drank acid.
They didn't drink it. They just mixed them together in front of themselves. Right? And then, in fact, actually, if they mixed it after having drank it after having mixed it, it probably wouldn't be that big of a deal. It's a neutralization reaction, so that's an interesting point. We do have a neutralization reaction. Okay? Also known as double replacement. Exact same thing. How do we know a chemical reaction occurred? Okay, it made water, but if I mix two things that are in solutions, yes, I make water, but I'm not making enough that I can visualize. How do we know there's a reaction, though? We have a salt, but salts are typically soluble in water. This one is. So I make these two solutions, I mix them together, and I end up with still a clear solution. So we can't see a change in phase. That's a good option. It's the last option. Heat, not taste. Let's get out of the taste mindset. That's a bad one. Okay? Heat. We get the formation or a release of heat because we made a covalent bond, technically polar covalent bond, with water. The formation of that new bond resulted in the loss of a lot of heat. Okay? So we can now start to classify these reactions as a heat source. That different observation means we now classify them a little bit differently, put some more information into them. So what we end up generating is this field of acids and bases. Arguably probably the easiest chemistry that you will see, and at the same time probably the most difficult, because it is everything that you do in general chemistry. It is everything that you do in organic chemistry, though it gets buried inside other molecules and everybody goes, oh, that's not acid-base anymore, until you bust out the definitions and go, oh yeah, that is. Okay? So what are our definitions? Well, the first approach to this, historically maybe, was looking at Arrhenius. Before you frantically write down this definition, just want to clarify that. We get two definitions from Arrhenius. Okay? Those definitions, okay, we're looking at taking that species and dissolving it in water. Okay? If we dissolve it in water and the concentration of hydrogen ions goes up, we call that an acid. Look at that, I even color-coded it, right? If instead we take that compound and we drop it into water and we see an increase in the concentration of hydroxide ions, we now have a base. Okay? I'm a little bit overstepping my bounds on calling it completely useless. It's not completely useless. And it works at a very simple level. The issue with that definition is that it is so narrow that we can't really apply it to anything. Okay? So that if we're trying to advance into further chemistry classes and we want to look at how bonds are made and broken, well, this really only works for the neutralization reaction, nothing else. If I want to describe how a double replacement reaction occurs, I now have to define a whole new series of compounds and formulas. That's a bit tedious to go through and deal with. Okay? So what we want is a broader definition. The first pass at that broader definition, after we sort of accept that these definitions are useless, is the Bronsted-Lowry definition. Okay? That definition, slightly tweaked to make things a little bit more inclusive. Instead of looking at hydrogen ion and hydroxide as two separate species, we go through and refer to a hydrogen or an acid as a hydrogen ion donor. Same thing as before. Okay? Exact same definition. Where our definition changes is when we move to the base. Now instead of looking at hydroxide, we look at a hydrogen ion acceptor. So what we're concerned about in this definition is the transfer of hydrogen ions from one molecule to another. If the one molecule gives up hydrogen ions, we're looking at an acid. If it accepts a hydrogen ion, it becomes a base. This definition helps us out a little bit with probably one of the more common bases that you may or may not have already worked with. Ammonia, when reacting with a strong acid, will generate NH4+. That is an acid-base reaction. If we looked at that reaction under the influence of the Arrhenius definition, we don't have valid rules because the ammonia does not have hydroxide, so it doesn't match that base definition. So this one expands that definition a little bit, helps us out. Okay? So those are our two big definitions within them. Would have been nice for me to tell the morning section this, but I'll tell you guys. You guys are better, right? Hydrogen ion, is there another name we could come up with? What makes a hydrogen atom? A hydrogen atom. What things make a hydrogen atom? I understand what you're saying now by saying hydrogen. That doesn't count. It has one proton and one electron. When we're looking at a hydrogen ion, what's the charge on our hydrogen ion? Hydrogen ion, so it can't be neutral because it's an ion. Plus or minus?
Plus.
Plus. How do we make a hydrogen ion positive?
Taking away the electron.
We need to ditch the electron. If we get rid of the electron, what's left? A proton. Instead of referring to it as a hydrogen ion donor, one of the common ways you'll hear it is a proton donor. Okay? Be a little bit careful with that. We're not changing atomic structures in this case. So it's not going into the nucleus when we form a new bond. We're just saying that that extra proton is now floating on the outside of the structure. Okay? So we can hear hydrogen ions also referred to as protons. So our acids can be proton donors, our bases can be proton acceptors. So let's take a look at a reaction here. The compound of interest in this case is actually a tricky one. Okay? This one ends up being tricky because it has hydrogen, which means it can act as an acid. What does a base need to do? Accept protons. What charge was a proton? Positive. So what charge do you think a base would be? What charge is this species? Negative. This species has a very special property. It is what is known as an amphoteric compound. Amphoteric because it can act as both an acid and a base. Okay? So, what's that? No, water can actually do the same thing, but that's a more difficult concept. There's lots of amphoteric compounds. Okay? So let's make that a little bit simpler. Let's say it acts as an acid. Man, that happened fast. What happened? What does that mean the water has to act as? A base. Okay? Which is one of the reasons why these definitions are nice. If I find a base, what does that mean it's reacting with? An acid. If I find an acid, it reacts with a base. Okay? So I can start to make some conclusions about what's going to occur in a reaction. What does an acid do? I know it was one slide ago, but hopefully you can remember that. What's the definition of our acid? Slide 16? What? Sour tasting, no. Donates hydrogen. We're looking at a hydrogen ion donor. All right, what's the definition of our base?
Hydrogen ion acceptor.
A hydrogen ion acceptor. So what can we do with that information? We can now predict the products. If our acid loses a hydrogen, what's left? So it's, our acid is HSO3 minus. If I get rid of a hydrogen, what's left? SO3. Okay, you're saying sulfite. Why are you saying sulfite? Okay, so you're also implying something else. If I just wrote SO3, that's sulfur trioxide. You are right, it is absolutely sulfite. What's the difference between SO3 and sulfite? Charge. In the course of this reaction, we gained another negative charge and became sulfite. And remember, it's an H plus that is lost. So we lose a positive charge, which means it needs to become more negative. So we get SO3 minus 2. What happened to the water? H2O acted as a base. It gained a hydrogen, so we should get, for our formula, H3O. What was that? Plus. It started neutral and it gained a positive charge. It needs to be positive to account for that balance. So what we've now done is come up with a way to predict the products out of this reaction. Kind of a neat observation. As an extra little piece of information here, which gets us closer to ending, what's happening in the middle there? Is that a standard reaction arrow? No, it's a little bit different. Why is it different? What does that reaction arrow mean? The reaction can go both forwards, towards the right, and it can go backwards, towards the left. So what we could go through and do is now set up a new reaction where we have SO3 minus 2 and react that with H3O plus. SO3 minus 2 now acts as what? Okay, for it to act as an acid, what does it need to have? Hydrogen. Does it have a hydrogen? Nope. So what does that mean it's going to act as? A base. What's the other one going to act as? An acid. What do bases do? They accept hydrogens. Our acids lose hydrogens. We can now again predict what those products are by adding and subtracting a hydrogen from our structure, making sure to account from the charge. What answers do we get? The exact same that we started with before. Interesting. Okay? Which brings up the next question. Okay? We're talking about conjugate partners, the things that are most similar on opposite sides of the reaction. So let's pick this guy, HSO3 minus. What is most similar to it across the reaction? SO3 minus 2. We can now refer to those two compounds as conjugates of each other. Think of it as conjugal visits. Okay? In a conjugal visit, typically you're only allowed to be with people you have some relationship with. Okay? So we're looking at those two as our conjugate partners. HSO3 minus acted as what? An acid. What does SO3 minus 2 act as? A base. So when I start to pair these up, not only do we now have conjugates between these two, but one is an acid and the other one is a base. So I can now label these as conjugate base and conjugate acid. And we can go through and do that with all of these. The confusing, or one of the extra pieces with this, is because it's a reversible reaction, if I now ask you to tell me what is the conjugate base, and you need to now specify an atom, or sorry, a molecule or molecules, what is the answer to what is the conjugate base? It ends up being both the SO3 minus 2 and the H2O. Depending on which way our reaction went, we have different conjugate bases. This, in my opinion, is a massive flaw with the final. Okay, so if you were paying attention, you know exactly what I'm talking about within this. Okay, if not, good luck. Okay, you need to make sure that you understand what's happening within these conjugate partners. If we ask you to identify the base within an individual reaction, there are two bases. If I ask you to identify the acid, there are two acids, depending on which direction that reaction goes. That is a huge thing to watch out for. If I ask you to identify the conjugate acid, how many conjugate acids are there? Two, because it all depends on which way that reaction's going. Okay?
Is the conjugate always part of the product?
The conjugate is always part of the product of whatever the reaction is. So this is the conjugate acid because it is the product of these two reactants. This is the conjugate acid because it is the product, look at our arrow, of these two reactants. Snap, I hate that definition, by the way.
And these always go back and forth.
And they will, these reactions, so all chemistry goes backwards and forwards. Okay? It is such a confusing topic that I first off thought we shouldn't have talked about it at all in this class, but it's all over, or it's on part of your final. There's an entire semester devoted to this arrow, or this double-headed arrow, going backwards and forwards. Okay? It is known, or it is what is known as equilibrium. Okay? The rate of our forward reaction must equal the rate of our reverse. It says nothing about the concentrations, but it's looking at the balance of those two reactions. We can still have our products favored as far as an amount, or produce more products than we have reactants. But the speed of the reactions, once we get to equilibrium, must equal the same. Okay? So, where does this become really important? The big question that you guys need to understand is Le Chatelier's principle. Once we are at equilibrium, the reaction will do whatever it needs to maintain equilibrium. What does that mean? Okay, well, let's take a look at equilibrium as kind of a seesaw. We'll look at another example of it on whatever the next class is, Thursday. So let's pick the seesaw example first. Okay? If we look at a seesaw, we say this is now balanced, right? It is now at equilibrium. What happens, so let's say we've got everything set up in this case. Let's say I now go through and add some H3O+. That changes the concentration of the H3O+ on the product side, which means I now have more products. What happens to the seesaw? It gets out of balance. Okay, we're no longer at that level playing field. The reaction wants to be at that level playing field. In fact, it has to be there. So this is one of the kind of interesting, you could even call it artificial intelligence almost of all chemistry. We strive for that balance. And if we mess it up by tweaking some system with it, the reaction on its own will re-equilibrate. We'll reach that point where it's balanced. What does the reaction have to do in this case to make that happen? Okay, we're seeing some shifting, kind of the right idea. What we're going to do is we're going to take a chunk out over here, and we're now going to put it over here. So there's our piece. See how artfully done that was? And what's now happened is we've balanced out the concentrations. So if I increase the concentration of my products, what does my reaction do? It converts some of those products into reactants. What happens if I increase the concentration of the reactants? It's going to shift to favor the products, to get rid of those reactants and increase the products so that it can balance out. We'll end on the last kind of zinger of this. What happens if I remove some reactants? Okay, we'll pick up there on Thursday.